This is section 3.1, part C, measuring linear association, correlation. A scatter plot displays the direction, form, and strength of the relationship between two quantitative variables. Linear relationships are particularly important because a straight line is a simple pattern that is quite common. A linear relationship is strong if the points lie close to a straight line, and weak if they are widely scattered about the line. Unfortunately, our eye is not a good judgment on how strong a linear relationship is. The size and the scale of the drawing can change how well the data looks compared to the line. Since it's easy to be fooled by different scales or by the amount of space around the cloud of points in a scatter plot, we need to use a numerical measure to supplement the graph. Correlation is the measurement that we are going to use. So the correlation R measures the direction and strength of a relationship between two quantitative variables. The correlation is always a number that's going to be between -1 and +1. Correlations indicate the direction of a relationship by its sign. If your R value is greater than 0, then this means your data values have a positive association. And if R is less than 0, you have a negative association. Values of R near 0 indicate a very weak linear relationship. And the strength of the linear relationship increases as R moves farther away from 0 and closer towards either -1 or +1. The extreme values of R equals -1 or R equals 1 occur only in the case of a perfectly linear relationship, when the points lie exactly on a straight line. So here are some examples of some correlations. As you can see in this picture, these are completely scattered. There is no association. You can't tell if it's positive or negative. So this has an R value of 0. Now these points are coming down, but they are very scattered from the line. So you do know it has a negative association, but because it is so weak, the R value is closer to 0. These points are moving up, so there's a positive association, but again, those points are scattered from that line. We have a negative one here. They're getting close to that line, so the R value is -0.7. These are getting even closer to that line, so R is equal to 0.9. As you can tell, these are almost a perfectly straight line, so our R value, since it's going down, is a -0.99. Now, how to calculate that R value? Suppose that we have data on variable X and Y for n individuals. So you have a set of some number of individuals. The values for the first individual are X1 and Y1. The values for the second individual are X2, Y2, and you would keep doing this for all the values. The means and standard deviations of the two variables are X bar and S of X, and Y bar and S of Y for the Y values. So to find the R value, you're going to do 1 over n minus 1, where n is the number of values you have. And then you're going to do your first observation minus the mean over the standard deviation for your X times the Y first observation minus Y mean over the standard deviation of Y. You're going to add that to the second one, the third one, all the way through. Or you can compound this and you can write it as the sum of your X sub i's minus X bar all over S sub X times Y sub I minus Y bar all over S sub Y. And you're going to take that summation and multiply it by 1 over n minus 1. So the formula for the correlation R is very complex. It helps us see what correlation is, but in practice, you should use your calculator to find that R value. The formula for R begins by standardizing the observations. Remember, to find the standardized score, Z is equal to X minus X bar over S of X. So you are standardizing the X values, you're standardizing your Y values for each of your values, you're multiplying those two together, adding them all together, and then you are multiplying by 1 over n minus 1. The formula for R begins by standardizing. Let's use the familiar hiker data to determine the required calculations. The table below shows the values of body weight X in pounds and pack weight Y, also in pounds, for the 8 hikers. For these data, we know that our mean for the body weight is 136.125 pounds, and our standard deviation is 30.296. For the pack weight, the average weight is 28.625, and the standard deviation is 3.462. So here's our original data. We're going to take the means and the standard deviations, and we are going to find the z-score. So for the first hiker, we know that their weight is 120 pounds. We're going to subtract the mean and divide the standard deviation, and we're going to get a z-score for that x value of negative 0.53. Then we're going to do the same thing for the y. So for the first person, their pack weight is 26. You'll subtract the mean pack weight divided by the standard deviation, and you'll get the z-score for the y. When you multiply the hiker's two z values, the value will become positive. The correlation R is an average of the products of the standardized scores for all hikers. Just as in the case when we were dealing with the standard deviation S of x, the average here is divided by one fewer than the number of individuals. If we finished all these calculations, we added them together, we multiplied by 1 over n minus 1, you would get an R value of 0.795. Some people like to write the correlation formula as 1 over n minus 1 times the sum of z sub x times z sub y. This is the exact same thing. We're just trying to emphasize the point in there that it's actually the standardized value for the x and the standardized value for the y. But good news, your calculator can do this calculation for you. So to do this, you're going to input your x values into list 1, input your y values into list 2. Then you're going to hit second y equals, which is your stat plot, and you're going to turn on a stat plot with a scatter plot. If you hit zoom and then zoom stat, which is option number 9, this will graph your information for you. It'll make your scatter plot. Now you do need to go to mode and scroll down and check to see if your stat diagnostics is turned on. If it's not, go ahead and turn it on now. Then you're going to hit Stat, go over to Calculate, and select Linear Regression A plus BX. Make sure that your X list is L1 and your Y list is L2. You can go down to Store Reg Equation. If you hit Vars, go over to Y Vars, select Function, and then select Y1. It will actually input your linear regression line into your Y equals so you can then graph it on your scatter plot. Once you hit enter, you will see the equation for your linear regression line, and you will also see your R value, which is your R correlation. Now, if you go back to your graph, you will see that line graphed onto your scatter plot. So the scatter plot of the body weight and pack weight for the 8 hikers is below. For these data, we know that the R value is 0.795. So we need to interpret the value of this R value. The correlation of 0.795 confirms what we saw when we looked at the scatter plot ourselves. There is a moderately strong positive linear relationship between body weight and pack weight for our 8 hikers. What effect would removing the hiker with the heaviest body weight from the data set have on the correlation? So if we took this point away, what would happen? By removing that outlier, we would increase the correlation because the rest of those points are actually now closer to the line or clustered closer to our linear pattern. So on your AP exam, if you are asked to interpret a correlation, start by looking at a scatter plot of the data. Then be sure to address the direction, the form, the strength, any outliers, and then put your answer back into context. Be careful. A value of r close to 1 or -1 does not guarantee it is a linear relationship. So you always need to plot your data points and look at it, because a scatter plot with a clear curved form can have a correlation that is near 1 or -1, but it doesn't mean it has linear association. So what does correlation actually mean? The calculator screenshot below provides more detail. The scatter plot of the hiker data have two lines added. We have a vertical line right here that is showing you the average body weight of your hikers, and you have a horizontal line right here that shows you the average pack weight for all the hikers. Now, most of the points fall in either the upper right quadrant or upper right quadrant or lower left quadrant, because they're either going to be above average with above average pack weight or below average body weight with below average pack weight. This should make sense. So how a correlation behaves is more important than the details of the formula. So here's what we need to know in order to interpret the correlation. Correlation makes no distinction between explanatory and response variables. So that means if you took your two and you switched them, the correlation would not change. Because R uses the standardized values of observations, R does not change when you change the units of measure for X, Y, or for both of them. The correlation R itself has no units of measurement. It's just a number. Describing the relationship between two variables is more complex than describing the distribution of one variable. Here are some causes to keep in mind when you are using correlation. Correlation requires that both variables be quantitative. Correlation does not describe curve relationship because between the variables, no matter how strong the relationship. A correlation of 0 does not guarantee there is no relationship between the two variables, just that there's no linear relationship. Like the mean and standard deviation, the correlation is not resistant, so R is strongly affected by any outliers that you have in your observations. And correlation is not a complete summary of two variable data. You should give the mean and standard deviations of both X and Y along with your correlation. So let's check our understanding. The scatter plots below show 4 sets of real data. In figure A, this is repeats of your manatee plot from before, so the increase of boats registered, increase of manatees killed. Picture B shows the number of named tropical storms and the number of predicted before the start of the hurricane season each year between 1984 and 2007. Plot C is the healing rate of micrometer per hour for 2 front limbs of several newts in an experiment. So how fast are they healing? And D shows stock market performance in consecutive years over a 56-year period. So for each of these, we need to estimate an R value, then interpret the value in context. So in the boat and manatee problem, we definitely have a positive association, and those are pretty close to a line. So we would say an R value close to about 0.9. On B, you can see that it is still positive, but they are much farther away. So we would have a positive R value, but it's going to be a lower number. So we could say this one is about 0.5. On C, once again, they are going up. As you move to the right, the values are moving up, but these are even farther away from the line. So we can have an R value of around 0.3. And on D, the values are going down. They are scattered, but not as scattered as the 0.3. So we could say these are around negative 0.5 or about negative 0.6. The scatter plot in picture B contains an outlier. This is the disastrous 2005 season, which had 27 named storms, including Hurricane Katrina. What effect would removing this point have on the correlation? And explain. So if I were to remove this point right here, the correlation would actually decrease, because this point has the effect of strengthening that linear relationship. It's showing that it's pulling it up. So by removing that point, you would actually be decreasing your correlation.